So for Lewis dot structures, we're going to start with the linear type, which is typically non-polar because the equal distribution of lone pairs repels each other and cancels each other out on both ends of the dipole. Most of the structures on this poster are going to be single bonds, which means they are also known as sigma, but we'll get into pi bonds a little bit after. So to draw a Lewis dot structure, you have to count up all the valence electrons in all the atoms, and then try to make it symmetrical as possible and equally distribute all the electrons. So for the polar water molecule, we have 6 valence electrons in oxygen and 1 in each of the hydrogens. So added up, that's 8 valence electrons, and through VSEPR theory, we know that there are 2 lone pairs on top of the oxygen and 2 sigma bonds to the hydrogens, which make up 8 electrons because the single bond is a makeup of 2 electrons being shared. We'll look at the trigonal, planar, and tetrahedral types. So for boron trichloride, it has 3 sigma bonds, and as those 3 bonded pairs, or bonded atoms, repel each other, it creates a 120-degree bond angle between these 3. And you check the valence electrons and see that boron has 3, chlorines have a total of 21, so 24 valence electrons in total, and you have 6, 6, 6, and then 2, 2, 2, and that is 24. Tetrahedrals are one of the more common molecules to see in a Lewis dot structure. It's just hard to visualize because these 3 are like a tripod stand, and you have 1 bonded pair on top. Okay, so now we're moving on to some of the more complex structures. This is better looked at as a 3D model because it has a thing called equatorial and a thing called axial plane, where this makes up a triangle. So the complete structure, molecular geometry for this structure is a trigonal bipyramidal, because these 3 are on a plane where it's like flat coming out of the phosphorus, and that makes a triangle, and bonded with the axial 2 fluorine atoms, that makes a pyramid coming up this way and a pyramid going down this way. Same for the sulfur hexafluoride, because it has 4 fluorine atoms on the equatorial plane, so the square that comes out of the sulfur atom, so sulfur central atom, and that creates a square pyramid this way and a square pyramid the other way. So a general rule of thumb is that most central atoms can only hold 8 electrons, and that is completed octet where the atom is satisfied with its count. However, for the bipyramidal structures, you may have noticed that the central atom held more than 8 electrons bonded to it or shared with it, and that's because of the expanded octet rule. So this rule states that every element past the phosphorus on the periodic table is able to invoke the ability of the d orbitals in the next period, which allows them to hold more than 8 electrons. Circling back around and looking at some of the bond angles for these different Lewis structures, a tetrahedral, because of its awkward positioning of the atoms in relation to one another, it is actually at a 109.28 bond angle between each chlorine. For the trigonal bipyramidal structure of phosphorus pentafluoride, we just look at the equatorial plane and see that it's a triangle, so these in relation to one another repel each other equally at a 120-degree bond angle, whereas the fluorine in relation to each one of these equatorial Fs is at a 90-degree angle. Same for the sulfur hexafluoride, except for the square on the equatorial plane has everything at a 90-degree angle. So one thing that should be considered when looking at Lewis structures is the topic of resonance. Resonance has to do with additional pi bonds, or otherwise known as double bonds. Double bonds are stronger than single bonds and also shorter. So taking a closer look at this double bond and this single bond, the stronger bonds are going to be much shorter than the longer single bonds, and they also require more energy to break, since bond forming is an exothermic process. So resonance is, by definition, the different ways that you can draw a structure that has double bonds. So this structure up here is the same as this one, it's just that the double bonds are placed in different places.
Teacher, I need some help on this problem. Teacher, come here. So to finish this off, I've got 4 electrons left right here, right? So to do it right, I'm gonna put 1 electron on each fluorine, correctly?
No. Billy, xenon needs to have 2 lone pairs to cancel each other out on the equatorial plane.
It would. Does MG stand for Madagascar?
No, that's molecular geometry. So that's when you describe the shape and the structure of all the atoms in a Lewis structure.
Who's Lewis?
Mg and Eg are molecular geometry and electron geometry. So for molecular geometry, you only take into account the atoms that are a part of the Lewis structure. So here we have 4 fluorines and 1 xenon, and that creates a tetrahedral molecular geometry. For electron geometry, we take into account the lone pairs as well. So since those 2 are ligands, we have 6 bonded pairs, and that creates a square bipyramidal geometry.
So, is the bond angle 20?
No, Billy, the bond angle is actually 90 in terms of the axial fluorines with the equatorial lone pairs and the equatorial fluorines.
So, can I make the assumption that this thing is polar?
So what Billy fails to see is that there is an unequal distribution of electrons on this Lewis structure, making it very polar.
Did I get a 100 on this?